So this is Cryptography Lecture 10. And what we started in Lecture 9 was the study of elliptic curves. We're starting with elliptic curves over the real numbers and the rationals, and we'll then move to elliptic curves over the finite field with p elements. But let's just review what we did yesterday, because this is somewhat new. So an elliptic curve is given by an equation of the form y squared equals x cubed plus ax plus b. And if you graph this curve in the plane, it typically has one of two shapes. In some cases, it has a shape that comes down and up and down, like that. And in the other case, it might have two components and look like that. So in the examples given in the text, if you look at the elliptic curve, y squared equals x cubed minus 3x plus 3, you get a curve that looks like that. Y squared equals x cubed minus 6x plus 5 gives a curve that looks like this. And we can notice that if P as a point with coordinate x, y lies on the curve, then also Px minus y lies on the curve, because if y squared equals x squared plus ax plus b, then minus y all squared equals ax squared plus x cubed plus ax plus b, because minus y squared is the same as y squared. So there's always a certain symmetry around the x-axis in an elliptic curve. If you have a point xy, you have the point x minus y. So if this is P equal xy, what I might call minus P is the point with the same x coordinate, but the opposite y coordinate. And we impose one other condition on an elliptic curve, which is really the condition that says that this cubic doesn't have multiple roots. We don't have to worry about that in this course, but the condition is that the discriminant, which is 4a cubed plus 27b cubed, is different from 0. So this is what is called the discriminant of this cubic polynomial, and that should be non-zero. It's completely analogous to the fact that if you have a quadratic equation, you have a discriminant b squared minus 4ac, and if that's 0, then you have a multiple root. And in this case, it's actually an exercise, a homework problem, though it takes a little bit of work to show that if the discriminant is 0, there is a multiple root. So what is the point of this curve? The point of the curve is that there's a way to take the points on the curve and add them. So the points on the elliptic curve form an additive abelian group. Additive just means we're writing the group operation as addition. You could easily use multiplication or any other funny symbol for it. But it forms an additive group. And it's a little bit different from the additive groups we've seen before. Additive groups we've seen before, the integers mod p, multiplicative groups are the non-zero congruence classes mod p, and so forth. So the way one deals with an elliptic curve, we have the addition on the elliptic curve is defined by chords and tangents. So the points are the points x, y on the curve. That means that satisfy the equation. Okay? The equation is always y squared equals x cubed plus ax plus b for some a and b. And another point, which is called the point at infinity, and is the additive identity in this group. So how do you define addition on the group? If you have a point P and a point Q, and you want to add them, how do you define P plus Q? If P plus Q are different, you take the line through P and Q, and it crosses the curve at a third point R. And you take that point R, and you reflect it around the x-axis, you get a point R prime, and the sum of P plus Q is defined to be this R prime. So you take the chord through P and Q, it will always cut the curve at a third point. That's a clue. That's something that has to clue, which I take that point, the third point where the line and the curve intersect, reflect around the x-axis, and call this point R prime the sum of P and Q. This is in the case that P is different from Q, we use the chord through P and Q. If P equals Q, that is, we're adding P plus P, there's no chord through P and P, but what you do is you take the tangent line through P. It will cut the curve at some point, reflect that through the x-axis, and that's what the sum of P plus Q will be. Now, if it happens that you choose the point right here, where the tangent line is vertical, so this P, if this point is vertical, line is vertical, it's not going to cut the curve at any point. And in that case, we say that P plus P is this point at infinity. Oh. So this is all perhaps a tiny bit abstract. So let me see if I can do a problem. And I'll just pick one of the homework problems. So this is exercise 6.1, problem 6.1. No, exercise 6.1, in section 6. So we have the elliptic curve, E is y squared equals x cubed minus 2x plus 4. So in this case, A is minus 2, B is 4, and the discriminant, 4a cubed plus 27b cubed, minus 2 cubed is minus 8, times 4 is minus 32. 4 cubed is 64, plus 64 times 27. Whatever it is, it's definitely not 0. So this is a legitimate elliptic curve. And one point on the curve is the point 0, 2. Because by that x equals 0, 0 cubed minus 2 times 0 plus 4 is 4, which is 2 squared. So x equals 0, y equal 2 works. Another point on the curve is 3 minus 5. Let's just check that. We let x equal 3. 3 cubed minus 2 times 3 plus 4 is 9 minus 6. X cubed is 3, sorry. 27 minus 6 is 21, plus 4 is 25, which is 5 squared, but it's also minus 5 squared. So we're just shooting, so the 0.3 minus 5 definitely satisfies this equation. And we want to compute P plus Q. So let me do it, what you might say is the old-fashioned way. So roughly speaking, we have a picture that looks like this. Let's say the curve is something like that. And let's say this is P and this is Q. And I want to start off by taking the line through P and Q and seeing what is the third point R where that line intersects the curve. So this is the elliptic curve, and this is the line, L. So what is the equation of the line? It's the line through P and Q. Well, the line through P and Q, so the line PQ has, what is the slope? The slope is 2 minus 5 over 0 minus 3. So that's minus 7/3. Okay. 2 minus 5 is 7, 7/3. So it's a line with slope 7/3 going through the point 0, 2. So the line L has the equation y equals minus 7/3 x plus 2. This has slope minus 7/3, and when x is 0, y is 2. When x is 3, y is minus 5. So this is definitely the line. So I can take this line and plug it into my equation. So what are the x coordinates of points where the line and the curve intersect? So y squared minus 7 over 3x plus 2 squared has to equal, well, what is this? Let me just multiply this out. This is 49 over 9x squared minus 28 over 3x plus 4 equals x cubed minus 2x plus 4. I have to solve this equation for x. So this is the same as x cubed minus 49 over 9x squared. I have 28 over 3 minus 2, so which is 28 minus 6. So that's plus 22 over 3x, and the 4's cancel equals 0. So I need to solve this equation. And let me just check. X equals 0 works. When x is 3, I get 27 minus 49 is minus 22, plus 22 is 0. So this certainly has roots 0 and 3. I want to find the third root. Let's see. So this is 0 equals, let me see if it gets simpler if I factor out x over 9. So this is x over 9 times x squared minus 49x plus 66. See, is that right? X cubed, sorry, 9x squared. 9x squared, x over 9. 49 over 9x squared. 22 over 3x equals 0. Let's see. This has a root 3, we know. So if I divide x, so this will factor. So this will be see, x over 9, x minus 3. So this has to be x minus 22. Let's just check. X squared doesn't look good. Let's see. Oh, 9x squared. Let me do it slightly different. So this is x times x squared minus 49 over 9x plus 22 over 3. But this will have a root of 3. So this is x times x minus 3 times x minus, and this is going to have to be 22 over 9. So let me just check. X squared, 60. My writing is so bad, it's hard for me to see. X squared, so plus 22 over 3, and this is 22 over 9, and this is correct. Okay, so the third solution of this equation is x equal 22 over 9. And when x is equal to 22 over 9, y squared is x cubed, 22 over 9 cubed, minus 2 times 22 over 9, plus 4. So what is that? You take a big piece of paper, or you can use a calculator, or you can use a computer. It's choice is completely up to you. So let's see. 22 over 9 cubed minus 2 times 22 over 9, which is 49 over 9, plus 4 is equal to 10,000 over 729. 10,000 is 10 to the 4th, or 100 squared. 729 is 9 times 81. That's 9 cubed. 981 over 9 cubed. So if this is correct, y is equal to 100. So 9 cubed, this is 100 squared over 3 to the 6th, which is 27 squared. So y is equal to 100 over 27. So if this is the point P, coordinate 0, 2, and this point Q is 3 minus 5, then the point R is 22 over 9, 100 over 27, and then you reflect that around the x-axis, you get 0, 2, 3 minus 5, the third point on the curve, 27 over 9, 100 over 27. You reflect that, you get the point 27 over 9 minus 127. And that is the sum of P and Q. So that is how you do addition of two separate points. And other cases, when you add P plus P and so forth, are the rest of the exercise. So that's just to give another example of calculating the sum of 2 points on a particular elliptic curve. Now, it's a lot of work, and it would be nice to have a formula for the sum of 2 points on the curve. And by a miracle, in fact, we do. So let me first summarize properties of addition on an elliptic curve. I have to add, if you're interested in mathematics, the study of elliptic curves is a huge part of mathematics. They're extremely interesting. There are a huge amount of time is going into studying them and so forth. Okay, so what are properties? First of all, we have this point at infinity, O, and if you add the point at infinity to P, P plus O, or O plus P, that's always equal to P. So this point at infinity, that's just what we call it. So it's nothing mystical. It's the identity in the additive abelian group that we're studying. Second, you take P plus minus P. What is minus P? If P is the point xy, then minus P is the point x minus y. And we know that xy is on the curve if and only if x minus y is on the curve. So P and minus P are points on the curve, and P plus minus P is the identity. Third, which is associativity, says if you add P plus Q and then R to that, that's the same as adding P to Q plus R. So this is the associative law. Associativity. And fourth, addition is abelian. P plus Q is always equal to Q plus P, which you can see immediately from the chord tangent process. Of course, the line through P and Q is the same as the line through Q and P. So this you can take of as a definition of how O works. This is clear, and this is what is hard to prove, and we'll come back to that. All right. Now, the miraculous result is, so this is theorem 6.6. It's the elliptic curve addition algorithm. So you have your elliptic curve, E, given by the equation y squared equals x cubed plus ax plus b. And we have points P1 and P2 on the curve. So I want to define P1 plus P2. If P1 is the point at infinity, then P1 plus P2 is just P2. It's A. B. If P2 is the point at infinity, then P1 plus P2 is P1. This is just the identity. If P1 is not the point at infinity and P2 is not the point at infinity, then they have coordinates. You can write P1 as x1, y1, and P2 is x2, y2. You only can do this if P1 and P2 are not the point of infinity, which is all the points except the point of infinity. Now, if x1 equals x2 and y1 is minus y2, then P2 is minus P1. So P1 plus P2 is the point of infinity. Otherwise, so this is in the case when it's not, when P1 is not minus P2. So otherwise, define a certain number lambda as follows. It's y2 minus y1 over x2 minus x1. That's like the slope of the line between the 2 points. P1 is different from P2. And if P1 equals P2, that is, they're the same point, then you define this to be 3x1 squared plus a over 2y1. And then we let x3 equal lambda squared minus x1 minus x2, y3 equal lambda times x1 minus x3 minus y1. And then the sum of P1 and P2 is equal to the point x3, y3. These are the coordinates. So these are sort of the trivial cases when one or the other of the points is the point of infinity. So the only interesting case is when you take 2 points, P1 and P2, which actually lie on the curve. If one is the negative of the other, the sum is 0. Otherwise, because they could be equal. If they're equal, this is what lambda is. And this is the formula. So how do you prove this? So it's almost the way I solved a particular case at the beginning of the homework exercise. One of the very first thing today. So this is really what we have to prove. So what was it that I did when I solved a particular problem? We had 2 points, P1 and P2, and I found the equation of the line through those points. And the first thing I did was say that the slope of the line through P1 and P2 is y2 minus y1 over x2 minus x1. And that is the number that is being called lambda in the text. So the line through P1 and P2, this is the slope. So using point slope formula, it's given by y equals lambda x minus x1 plus y1, which is lambda x plus y1 minus lambda x1. And we let nu be equal to y1 minus lambda x1. So this is y equals lambda x plus nu. So this is the slope lambda. Nu is the number that you need to choose for the y-intercept so that this line goes through the points P1 and PQ. And then you substitute this into the equation, exactly what I did in this special case. So you get lambda x plus nu squared is x squared plus ax plus b. X cubed plus ax plus b. So you get lambda squared x squared plus 2 lambda nu x plus nu squared equals x cubed plus ax plus b. So you get x cubed minus lambda squared x squared plus a minus 2 lambda nu x plus b minus nu squared equals 0. So the points of intersection of the line and the elliptic curve have x coordinates that satisfy this. And this is going to be equal factor. X1 and X2 are two roots, X minus X1, X minus X2. And we call the third root X3. So if you multiply this out, what do you get? You get X cubed. What's the coefficient of X squared in this? Coefficient of X squared is going to be minus x1 minus x2 minus x3 x squared plus some other stuff. So this is the coefficient of x squared, and this is the coefficient of x squared. So x1 plus x2 plus x3 equals lambda squared. So x3, which is the coordinate we're trying to find, is lambda squared minus x1 minus x2. That's what we said in the theorem. X3 is lambda squared minus x1 minus x2. So this is x3 and y3. Y is lambda x plus nu. So y3 is lambda x3 plus nu. Nu is y1 minus lambda x3. So I could also write this as lambda x3 plus y1 minus lambda x1. So this is lambda y3 is lambda x3 plus nu. Nu is y1 minus lambda x1. So this looks like lambda, oh yeah, this is right, lambda x3 minus x1. So minus lambda x1 minus x3 plus y1. So the coordinates of this third point are exactly this, and this is exactly right. Lambda x3 minus x1 plus y1. So minus y3, you reverse the sign of the y coordinate, is lambda x1 minus x3 minus y1. And this is the second coordinate up there. Okay. So we've been solving elliptic curves over the real numbers. But in cryptography, and in a lot of mathematics, we also look at elliptic curves over finite fields. So everything is exactly the same, except instead of looking at real numbers to satisfy the equation, we're looking at congruence classes mod p. This is z mod pz. So let's just consider odd primes. So definition. We take an odd prime p, and p greater than or equal to 3, an elliptic curve over fp. It's an equation of the form y squared equals x cubed plus ax plus b, where a and b are elements of this finite field, and in the finite field, 4a cubed plus 27b cubed is different from 0. And the set of points on the elliptic curve is E of fp. This is a set of all points x, y in fp squared, that is ordered pairs of points in fp, such that y squared is x cubed plus ax plus b, and the point at infinity. You're still at a point in infinity in the finite field case. So we start with an example. Let's take p equal to 13 and consider the curve E, which is y squared equals x cubed plus 3x plus 8 in F13. So my A is 3, my B is 8. So 4a cubed plus 27b squared 27 is the same as 1 mod 13. So we're doing all this calculation in F13. This is 4a cubed plus b squared. A is 3, so that's 4 times 27 plus 64. This is 81 plus 64. Actually, a cubed 27 is 1 mod 13. So this is the same as 4 times 1. And 64 is minus 1 mod 13. So this is 3, which is not 0 in F13. So we just do this calculation mod 13, we get 3. The point isn't really that we don't get 0. So what are the points on the elliptic curve? Well, we have to calculate. Calculate mod 13. So in F13, looking at the curve, y squared equals x cubed plus 3x plus 8. Let's make a table. So for the different values of x, what are the values of x mod 13? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And what is x cubed plus 3x plus 8? So when x is 0, this is 8. When x is 1, this is 1 plus 3 is 4 plus 8 is 12, which is the same as minus 1, mod 13. When you have 2, you have 8 plus 6 is 14, plus 8 is 22, which is the same as 9 mod 13. Right, let me just put it here. I'll do it here and I'll put it mod 13 so it's somewhat easier to see. So this is 12. 8 is 8 mod 13. 12 is 12 or minus 1 mod 13. 2 cubed is 8 plus 6 is 14, 22. Mod 13 is 9. 3 cubed is 27. Plus 9 is 36. Plus 8 is 44. Mod 13, I think that is 5. 4 cubed is 64. Plus 12 plus 8 plus 20. So that's 84. Let's see, 13 times 7 is 91. 13 times 6 78. So this is 6. When x is 5, you get 125 plus 15 plus 8. That's 148. Mod 13, 130. Yeah, well, that's also 5. 6 cubed is 216 plus 18 plus 8 plus 24 is 240. I think that's 6 mod 13. 7 cubed is 343 plus 21 plus 7 is 371. Divide that by 13. Get minus 19 minus 6. x cubed, 7 cubed is 7 times 49, that's 343, plus 21 is 364, plus 8 is 372. Let's see, 343, 351, 372. You divide that by 13, that's like minus 18, minus 5 is 8. See, when I got 2 here, oh, 8 plus 6, 14 plus 8 is 22. That's 9. Oh, that's all right. Let's see, 8 squared is 64, which is minus 1 times 8 is minus 8. Plus 8 is 0. 3 times 8 is 24. Let's see, that's 11, I think. 9 cubed is 729 plus 9 times plus 27 plus 8 is 35. 4, 6, 7. This might be 10. Yeah. Let me just pause the calculation for a minute. Let me just go through and make sure it's clear what we're doing. We have the curve y squared equals x cubed plus 3x plus 8 in the field with 13 elements. So I want to find all the points that satisfy this equation. So let's see. When x is 0, y squared has to be 8. So what is congruent to 8 mod 13? So y squared equals 8 is the same as y squared congruent to 8 mod 13. What are the squares mod 13? You have 0 squared, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 is minus 6, 8 is minus 5. It's really plus or minus 1 squared, plus or minus 2 squared, and so forth. When you square these numbers, you get mod 13. You get 0, 1, 4, 9. 16 is 3. 25 is minus 1, or 12, minus 1. 36 mod 13 is minus 3, or 10. Minus 1 is the same as 12. So 8 is not on this list. So y squared equals 8 has no solution. So when x equals 0, there's no y that satisfies this equation. What about when x is equal to 1? When x is equal to 1, y squared is going to be 1 plus 3 plus 8 is 12. 12 is equal to 5 squared and also minus 5, which is 8 squared mod 13. 25 minus 12 is 13. 64 minus 12 is 52, which is 4 times 13. So when x is equal to 1, you have 2 points on this curve. 1 and 5, and 1 and 8. What about when x is equal to 2? When x is equal to 2, we have to find y squared equal to 8 plus 16 plus 4 equal to 22, which is or congruent to 22, which means congruent to 9 mod 13. Well, plus or minus 3 is congruent to 9 minus 13. 3 squared is congruent to 9, and 10 squared is congruent to 9 mod 13. 9 minus 9 is 0. 100 minus 9 is 91, which is 7 times 13. So for x equal 2, we get 2 more points on the curve. 2, 3, and 2, 10. What about when x equals 3? When x is equal to 3, y squared has to be equal to mod 13. 3 cubed plus 3 times 3, 9 plus 8, which is 27, 36, 44. So y squared has to be congruent to 5 mod 13. And if you look at the squares mod 13, there's no 5. So there's no solution. And you keep checking, x equal 4, 5, 6, 7, 8. There's no solution. When x is equal to 9, y squared has to be equal to 9 cubed plus 3 times 9 plus 8 mod 13. Let's see, what is that? 9 cubed. 9 is the same as minus 4. So it's like minus 4 cubed plus 27 plus 8. Minus 4 cubed is minus 64. 27 is 1 plus 8. Minus 65 is 5 times 13. So this is 1. This is congruent to 10 mod 13. And we have a number, 6 squared is congruent to 10 mod 13, and also 7 squared. So when x is equal to 9, you get the points 9, 6, and 9, 7. So 2, 4, 6. It turns out there are 2 more points, 12, 2, and 12, 11. And there's also always the point at infinity. So this curve, mod 13, has 2, 4, 6, 8, has 9 points. So there are 9 points on the curve. And we're going to use the same kind of algebraic rule for adding 2 points on this elliptic curve over the finite field. So addition on the elliptic curve E over the finite field FP, and we're going to use exactly the same formula we worked out for adding the curve over the wheels. So in that theorem, which is 6.6, if you take a point P1 with coordinates x1, y1, and P2 with coordinates x2, y2. When P1 is different from P2, we're going to get P1 plus P2 is the point x3, y3, where x3 is given by the formula lambda squared minus x1 minus x2. Lambda is what would be the slope of the line through these 2 points, y2 minus y1 over x2 minus x1. And the second coordinate is lambda x1 minus x3 minus y1. So when these are different points, this is the formula for the sum of the 2 points on the elliptic curve. You don't have to memorize that because you always have your book in front of you or the notes in front of you, and all the exams are open book exams, so it's always written down for you. And in the special cases where one of these is the point at infinity and so forth, it's always p plus 0 is p, and p plus minus p is 0, and so forth.
Professor, so we can use this formula to solve like because I remember for the homework like 6.1.
Yes.
Okay.
So
So we could
6.1
hmm
was solving the elliptic curve over the real numbers,
hmm
but it turns out when you're solving over a finite field, the algebra is the same, and you come up with exactly the same formula. This is the solution in FP. So now we're looking at the finite field curve and not the curve over the reals.
Okay.
Okay. So let me just do a sample calculation. We have this elliptic curve, y squared equals x cubed plus 3x plus 8 over the finite field with 3 elements. So and we have the points p equal 9, 7, and q equal 1, 8. So I want to compute p plus q over this elliptic curve. So my slope, equivalent lambda, which is y2 minus y1 over x2 minus x1, is 8 minus 7 over 1 minus 9, which is 1 over minus 8. Now we're doing arithmetic mod 13. Minus 8 is the same as 5 minus 13. Minus 8 is congruent to 5 mod 13. What is the inverse of 5 mod 13? Let's see, 5, 10, 15, 20, 25. 5 would be minus 1, 5, 8. 5 times 8 is congruent to 1 mod 13. So 1/5 is 8 mod 13. So this is 8. So lambda is equal to 8. Nu is y1 minus lambda x1. Y1 is 7 minus lambda, which is 8, times x1, which is 9. So this is 7 minus 72, which is minus 65, which is minus 1. No, sorry, which is 0 mod 13. So lambda is 8. Nu is 0. So x3 Actually, I didn't even need the new for this, but x3 is lambda squared minus x1 minus x2. Lambda squared is 64 minus 9 minus 1 is 54. Mod 13, that's 2. Y3, it could be, this is minus lambda x3 plus nu. So minus lambda is 8, x3 is 2, nu is 0. This is minus 16, which is 10, mod 13. So,
Excuse me, Professor, what is nu again? Because I know like lambda, but what is nu again?
um, so in the theorem that we use, let me just find out where I wrote it down. Nu is y1 minus lambda x1.
Mm-hmm. And is nu always gonna be like that in?
Yes, yeah. Lambda is this,
Mm-hmm.
and nu is this.
Okay.
In the case when P1 is different from P2, um, there are some special cases that you have to worry about sometimes, but it's all explicit in the text, right?
Mm-hmm.
So we get
So
210. So in the way you would write this algebraically is 9, 7 plus 1, 8 on the elliptic curve is 210. Sorry, yeah. 9, 7 plus 1, 8 is 210. Well, 1, 8 plus 9, 7 is 210. Now, the interesting thing is to try to calculate how many points are on the elliptic curve over FP. So let's say we take an elliptic curve, y squared equals x cubed plus ax plus b in the finite field with b elements. So for each x, compute x cubed plus ax plus b, and we're doing everything mod p. So this is some number. And for the reals, if this were like a number, whatever number it was, you want that to be y squared, so y would be the square root of that. So the question is, let's call this for the moment, I'll just call this y. Does there exist a y in FP such that y squared is congruent to r mod p, right? This has to be, not everything is a square, right? We saw mod 13, some numbers weren't squares. Let's take a simple example. If I take p equal to 5, so I'm looking at the finite field with p elements, what are the squares? 0 squared is congruent to 0, mod 5. 1 squared is congruent to 1. 2 squared is congruent to 4. 3 squared is 9 is congruent to 4. 4 squared is congruent to 16, which is congruent to 1. So the squares mod 5 are 0, 1, and 4. If a number, so 2 is not a square and 3 is not a square. So y squared congruent to 2 mod 5 and y squared congruent to 3 mod 5, these have no solution. So if you have your elliptic curve over a field with 5 elements, and for some x, x cubed plus ax plus b is 2, there's no point on the elliptic curve with x equal 2, because there's no point, there's no number y such that y squared is equal to 2 mod 5. So you can always calculate x cubed plus ax plus b. What's not clear is for which of those numbers is a square. Just as for historical purposes, if nothing. If y squared congruent to r mod p as a solution, then y is called a quadratic residue mod p. And if you look at the numbers mod p, you have 0, 1, 2, up to p minus 1. They're p minus 1 non-zero congruence classes or elements in FP, and exactly half are squares, or exactly half are quadratic residues. So if you pick a number at random, a non-zero number, mod p, the probability that it's a quadratic residue or a square is a half. Half of the congruence classes are squares, and half of the congruence classes are not squares. So if you choose x at random from the numbers 1 up to p minus 1, half the time it will be a quadratic residue, and half the time it will not be a quadratic residue. So for p minus 1 over 2 choices, you will have a quadratic residue. And each time you have a quadratic residue, you can solve y squared equals r. Then minus y squared is also equal to r. So you'll have 2 solutions. So you'll have roughly 2 times p minus 1 solutions for your elliptic curve, plus the point at infinity. So if you want to know approximately the number of points on an elliptic curve, it's stated as the following theorem, which is a highly non-trivial theorem to prove, due to a German mathematician named Helmut Hasse. So you have E an elliptic curve over the finite field with p elements. So E of Fp is the set of points xy on the curve in Fp. These are not numbers, these are congruence classes mod p. So the number of elements in this on this elliptic curve is going to be approximately p minus p plus 1 minus something. This is just the way it's written, so it's traditional. Where this t sub p is fairly small compared to this. Where t sub p in absolute value is at most 2 times the square root of p. Let's try and do a calculation because this is really a kind of mathematics that you have almost certainly never seen before. Suppose I take the elliptic curve y squared equals x cubed plus 4x plus 6. And let's try and find the number of points on this curve over the field with 3 elements. So over the field with 3 elements, the only square, the field is 3 elements, 0, 1, and 2. 0 squared is 0, 1 squared is 1, 2 squared is 1. So the squares are 0 and 1. Let's see, suppose I take x equals 0, I get, so over F3, this curve is the same as y equals x cubed plus 4 is the same as 1 and 6 is the same as 0, x cubed plus x. So when x is 0, I get y squared equals 0. So one solution is 0, 0. When x is 1, I get 1 plus 1 is 2. 2 is not a square. When x is 2, I get 8 plus 2 is 10. 10 is the same as 1, and 1 is a square. It's either 1 squared or 2 squared. So on this curve, mod 3, we have these 3 points together with the point at infinity. So the number of points in F3 is equal to 4. What about p equal 5? In p equal 5, the quadratic residues are 0, 1, and 4. What are the solutions of this pairs xy when p is equal to 5? When x is 0, we would get y squared is 0 plus 0 plus 6 is 6, which is 1 mod 5. So we get the point 0, 1, and 0 minus 1. They satisfy this. When x is 0, you get 6, which mod 5 is 1, 1 squared minus 1 squared. Okay, when x is 0. What about when x is 1? When x is 1, we have to solve y squared equals 1 plus 4 plus 6, which is also 1 mod 5. 11 is 1 mod 5. So we get the points 1, 1, and 1 minus 1. What about when x is 2? We want to solve y squared equals 2 cubed plus 4 times 2 plus 6. That's 22, which is 2 mod 5. No solution. 2 is not a square. What about x equals 3? We have to solve y squared. If solution is mod 13, y squared equals 3 cubed plus 4 times 3 plus 6. That's 27 plus 18. What's 27 plus 18? 45, which is 0. So we get the 0.30. When x is 4, we have to solve y squared equals 4 squared plus 4 times 4 plus 6. That's 38, which is 3, and there's no solution. So for this equation, y squared equals x cubed plus 4x plus 6. Over the field with 5 elements, we have the solution 0, 1, 0, minus 1, 1, 1, 1, minus 1, 3, 0, and of course also the 0 at infinity. So the number of points over the field with 5 elements for this equation is 6. I should check that because I think I made a mistake. So when x is 0, there are 2 solutions. When x is 1, there are 2 solutions. When x is 2, 8 plus 8 is 16 plus 6 is 22. Is 2, there's no solution. When x is 3, 27 plus 12 plus 6. Oh, I'm sorry, 27 plus 12 plus 6. 27 plus, so that's the same as 7 plus 2. 27 plus 12 is 39 plus 6 is 45 is 0. Ah, we get a solution. Oh, well, I got a solution. X equals 3, y equals 0. Okay. When x is 4, I get 4 cubed. 4 cubed is 64 plus 16 plus 6. Mod 5, that's 1. So this has solutions 4, 1, 4, minus 1. So altogether, there are 8 solutions for this elliptic curve. Okay. Make one final remark. We have what is going to be called the elliptic curve discrete. Logarithm problem. ECDLP, the acronym of complex. So given points P and Q on the elliptic curve E, such that Q is n times P. This is addition. This means P plus P plus P, P added to itself n times. This is addition on the elliptic curve. So you know Q is n times P. You know Q is some sum of elements of P. Find n. So that's the discrete logarithm problem. You can't say, well, if Q equals NP divided by N, because you're not in the reals. This is hard. And this is the basis for several cryptographic schemes. So in the next talk, I'll talk a little bit more about this discrete logarithm problem.
Thank you.
Thank you,
Okay.
Professor.
All right, the next official talk is
Thursday.
Tomorrow is Juneteenth, and it's a holiday at CUNY. Campus is closed, and so on.
And Professor, so just to reiterate, we'll get our grades back tonight, and then we'll be able to
Well,
check
sorry,
tomorrow.
I hope we'll get. I'm not sure you're getting back tonight because I have another class that I'm also grading.
Okay.
So I'm further along in that one. That one I know will be done tonight. This one might not be done until lunchtime tomorrow.
Okay.
Okay.
So
But
around
basically, all I'm
tomorrow.
doing now is grading exams.
So like tomorrow we'll be able, at least by tomorrow, by the time the meeting comes out, we'll be able to like look at our exams grades and then compare it to like how we actually solve the problem and stuff like that, right?
Yeah, I hope so. Yes.
Okay.
Okay. All right. Bye all.
Thank you. Bye-bye.